Welcome to week 9 of Classical Mechanics 2. I'm Sabeta Matsumoto, and this week we're going to be talking about central force problems. In the last unit, we considered the Lagrangian and Hamiltonian formulations of mechanics. This week, we're going to use them to study a well-known problem, the two-body problem. While it's not necessary to use either the Lagrangian or Hamiltonian method to study these problems, as shown in this beautiful simulation by Evgenii Neumerzhitckii, but we will see several simplifications of the problem and novel phenomena that come out of these two approaches. Let's begin with the standard setup for the central force problem. Here, we have two particles. One has mass m1, located at distance r1 from the origin, and the other has mass m2 and is located at distance r2 from the origin. They're separated by some vector r is equal to r1 minus r2. The central force potential is a potential that depends only on r, so the separation between the two particles. In these coordinates, the Lagrangian would be given by 1/2 m1 r1 dot squared plus 1/2 m2 r2 dot squared minus the potential energy. However, these are not the best coordinates we could choose. It's perhaps more natural to consider coordinates given by this separation r, since the potential energy already only depends on that coordinate, and maybe the center of mass coordinate here, RCM. And this is really nice because these two coordinates now don't depend on our specific choice of origin. The center of mass is given by the weighted average of the positions of each of these two particles. This is m1 r1 plus m2 r2 divided by the total mass, which we're going to call m. Now, in terms of the relative coordinate r and our center of mass coordinate rcm, we can write our positions r1 is equal to rcm plus m2 over m times our relative position r. And similarly, our position r2 is now given by rcm minus m1 divided by the total mass times the relative position r. The potential energy is already a function of these two coordinates, as it depends only on the magnitude of the relative coordinate r. Now let's rewrite the kinetic energy to be a function of the relative coordinate r and rcm. The kinetic energy is 1/2 m1 r1 dot squared plus 1/2 m2 r2 dot squared. And now when we replace our definitions of r1 and r2 with these two terms, here we end up with 1/2 m1 times rcm dot plus m2 over m times r dot quantity squared plus 1/2 m2 rcm dot minus m1 over m r dot quantity squared. So let's expand this out. We end up with now 1/2 total mass m rcm dot squared plus 1/2 m1 m2 divided by the total mass m times the relative coordinate r dot squared plus cross terms. These cross terms end up canceling out. This term here, m1 times m2 divided by the total mass, is something that we're going to call a reduced mass. In this setup, our Lagrangian is now given by 1/2 m times rcm dot squared plus 1/2 mu times r dot squared minus u, which depends only on the magnitude of r. This Lagrangian looks like it's really two Lagrangians for two different particles. It looks like there's a particle of mass big M that's moving at constant velocity rcm, and there's another particle of mass mu that's moving in the potential u along some coordinate r. So our Lagrangian is now the Lagrangian for the center of the mass plus this reduced Lagrangian. And we call it reduced Lagrangian because mu is our reduced mass. Since the derivative of LCM with respect to RCM is equal to 0, we know that dl by drcm dot is a constant, so this is just the constant of integration coming from our Euler-Lagrange equations. And that means that RCM is an ignorable coordinate. For our reduced Lagrangian, we can look at the Euler-Lagrange equations there. So we've got dl by dr minus d by dt dl by dr dot is equal to 0. So these are just the standard Euler-Lagrange equations. From this, we know that minus the gradient of u minus the time derivative of mu r dot is equal to 0. Or equivalently, we have mu r double dot is equal to minus the gradient of the potential. This is the equation of motion for our reduced mass system. In this formulation, we've now reduced the dimensionality of the problem from a 6-dimensional problem where we have 3 coordinates for each of our R1 and R2 vectors to a 3-dimensional problem where we have just the 3 components of our relative position R. And in a moment, we're going to see that we can actually reduce this down to a 1-dimensional problem. This type of coordinate reduction is related to the symmetries in the problem. Here's a poster I saw a few weeks ago at a math conference. It's by Kat Movasegui, who's a master's student at the University of Toronto, Scarborough. In this poster, she's using the two-body problem of an example of how symmetries in the system, particularly when written in the Hamiltonian formalism, can lead to a reduced dimensionality of the system. And we'll return to this poster and these ideas in video 4 this week. In our system, we know that RCM is an ignorable coordinate. So we can choose an inertial reference frame where the center of mass is at the origin and the velocity of the center of mass is 0. In this coordinate system, our positions R1 and R2 are given by m2 divided by the total mass times the relative position R, and minus m1 divided by m times the relative position R. And these particles have velocities v1 and v2. In this coordinate system, our Lagrangian is merely the reduced Lagrangian, or 1/2 mu r dot squared minus u as a function of r. In this type of system, symmetry dictates that these orbits are planar. You can find some plane spanned by these vectors here, and that's the same as the plane spanned by these vectors here. So that means that the orbits of any of the particles in the system are always going to lie within a plane. So that means that a 2D representation is all we need. In 2 dimensions, we have our relative coordinate r is equal to r cosine theta and r sine theta, or we can write down the velocity of this squared as r dot squared plus r squared theta dot squared. So when we write out our new Lagrangian, we've got 1/2 mu times r dot squared plus r squared theta dot squared minus our potential energy. And you'll notice that theta goes to theta plus delta theta, doesn't change our overall Lagrangian. So Noether's theorem says that dl by d theta dot is equal to mu r squared theta dot is a conserved quantity of our system. And you'll notice that this is our angular momentum. So angular momentum is equal to I omega, which is mu r squared, and omega is clearly just the derivative of theta. That tells us that angular momentum is conserved, and that our constant angular momentum is going to be this term, L. Since we know that theta is an ignorable coordinate, that means our Lagrangian is really just a 1D system. The Euler-Lagrange equation, d by dr minus d by dt of dl by dr dot is equal to 0 gives the equation of motion for this whole problem. This originally 6-dimensional problem is now just a problem in this single dimension. This is equal to minus du by dr plus mu r theta dot squared minus mu r double dot. And our angular velocity, theta dot, is just equal to L, or the angular momentum, divided by the moment of inertia, or mu r squared. We can rewrite our equation of motion as minus du by dr plus L squared over mu r cubed minus mu r double dot is equal to 0. The force in the r direction is equal to L squared over mu r cubed minus du by dr. Let me re-express this term so it looks like the derivative of something. So I can rewrite this as d by dr of minus L squared over 2 mu r squared minus du by dr. And I can combine these two derivative terms together, and I end up with the force in the r direction is equal to minus d by dr of L squared over 2 mu r squared plus u as a function of r. And we're going to call this term our effective potential. This looks like we've got some extra potential that our particle is moving through. This is a little bit like a fictitious centrifugal force felt when you're in an accelerating reference frame. What does the effective potential look like? If we had a 1 over r squared force, we have a potential here. This would be in terms of like gravity or the electrostatic force that goes like minus 1 over r. Our centrifugal potential goes like 1 over r squared. That's a term like this. So when I add these two together, I end up with an effective potential that looks like this. So this is great because now we have a minimum to our effective potential, and this will give rise to lots of interesting dynamics, which we will see in the next video. The last thing we want to double check for this formulation is that we want to make sure that energy is still conserved in this new coordinate system. This is our equation of motion. We've got the force in the r direction minus the derivative of some potential. So if I want to make sure that this is conserved, what I'm going to do is I'm going to multiply both sides of the equation by r dot and then integrate this dt. On the left-hand side, I end up with 1/2 mu r dot squared. So this looks like a kinetic energy term. And then on the right side, I have the integral of minus d by dr u effective r dot dt. Rewrite d by dr as 1 over dr by dt times d by dt of u effective. So this 1 over r dot is going to cancel out with this r dot, and I'm left with minus the integral of d by dt of u effective dt. When I integrate this out, I end up with minus u effective plus some constant. So this tells me that my kinetic energy, so 1/2 mu r dot squared plus u effective, is equal to a constant. So this tells me that yes, in fact, energy in my system is conserved. In the next video, we'll examine specific orbits that come from the inverse square law potentials of gravitation and electrostatics. See you next time. All right, let's try this again. I never hit record and it went so well last time. Okay, so this is a little bit like the centrifugal,